Hello and welcome to Amateur Radio 101, where we're going to go over everything you need to know to get your technician license. There's 3 licensing levels: Technician, General, and Extra. We're just going to be going over what you need for the Technician level exam. Before we dive into it though, let's talk a little bit about why you would want to get your amateur radio license. Here is a diagram of Earth, and this is me right here. And I've got my little handheld radio that weighs less than a pound. And I'm actually able to communicate all the way around the world. It's portable, reliable, and you can do short, medium, and long-range communication. Here I'm bouncing some high-frequency waves off the ionosphere so that I can communicate really far. Recently I was on a mountaintop and I actually picked up some 2-meter band traffic that was over 100 miles away. That's really neat. What is great about amateur radio is it's built into a hardened infrastructure, meaning the radios and a lot of the repeaters and other infrastructure is protected such that if there's no power, they still have backup batteries or solar or something that keeps them going in the event of an emergency. So most of your radios and repeaters will still work, which leads us to emergency communication. If there's a natural disaster, say like a flood, earthquake, fire, you're still able to talk. Power outages, still able to talk, and even terror attacks. During the Boston bombing, my brother was running in that race, and I didn't hear from him for over 12 hours, so it would have been really great if we had radios. I would have been able to get in touch with him and find out that he was actually okay. Amateur radios are independent of cellular coverage, so they're great for outdoor activities. If you're up in the mountains or places with limited cell signal, you can still communicate with your friends and family. It's good for rural communication, same thing here. You don't need cell coverage, and then it's also good for fire and search and rescue applications. Alright, amateur radio is a voluntary licensed non-commercial communication service that is governed by the FCC, but daily operations are policed and administered by the end user, which is pretty unique. It's one of the last major self-regulated services in the United States. The amateur radio service allows various forms of communication, including Morse code, digital packets, voice talk, television, and more, all using radio waves across designated radio frequencies. If you've watched the recent SpaceX Starship launches, the video feed from the rockets are actually sent down to us in real time using radio waves in the 80-meter band. And we're going to learn more about these bands later and what that means in terms of frequency. The amateur licensing is broken up into 3 categories. You have Technician, General, and Extra. Technician will grant you the ability to start using your new radio in various frequency bands to communicate near and far under the right conditions. A newly minted amateur operator can communicate around the world. Let's talk about some of the basics of the theory here. First, I'm going to define what a transverse wave is. It is a wave that vibrates perpendicular to its direction of travel. So you have your wave here, and your direction of travel is right here. So in this case, it's vibrating or oscillating. Some examples of transverse waves that we can see are waves that the rope makes when you shake the end up and down repeatedly, or say waves on the surface of a lake when you throw a rock into it. That's a better 3-dimensional example. Electromagnetic waves are transverse waves that are made up of 2 components, an electric and magnetic field, and it vibrates through space at the speed of light, which is 300 million meters per second. Electric and magnetic fields are oriented perpendicular to each other and are also perpendicular to the direction of travel, making them transverse waves. This is not super important until later, but it is important to remember that you have an electric field and a magnetic field, and they're oriented at 90 degrees to one another. So what is the relationship between the electric and magnetic fields of an electromagnetic wave? The answer is they're at right angles. Alright, next up is polarization of a radio wave is defined by the orientation of its electric wave component. Again, so that would be this component is what is defining the polarization of the radio wave. Polarization is important when it comes to signal transmission. You actually have 3 different types of polarization. You have elliptical, circular, and linear. Polarization is going to come into effect later when we're talking about antennas. Electrical fields can take on different types of polarization. Okay, next we're defining wavelength. Wavelength is the distance from peak to peak of a wave. It's represented here by lambda. Frequency is inversely proportional to wavelength, or 1 over wavelength, and it's measured in something called a unit called hertz. Hertz is just 1 over seconds. When we read a frequency of 10 megahertz, we're saying it's 10 million cycles per second. The amplitude of a wave is the distance from the peak to the trough of the wave, and it's going to be represented by capital letter A. Something we're going to dive into shortly here is the difference between amplitude modulation and frequency modulation. We've got these two graphs here. Notice for amplitude modulation, the amplitude of the wave varies, but in frequency modulation, the amplitude remains constant, but the frequency or wavelength changes over time. All right, next we're going to talk about power. Power is measured in watts, and the formula is power equals voltage times current over here. And the three frequency ranges we're going to be concerned with, at least for our technician license, is going to be high frequency, ranging from 3 to 30 megahertz, very high frequency, ranging from 30 to 300 megahertz, and ultra high frequency, ranging from 300 to 3000 megahertz. You will need to memorize each of these, so something to bear in mind. I made a really nifty chart that I'll share with you at the end, and you can actually download it and keep it. Last thing here I'm going to say, radio frequency is defined as the rate of oscillation of electromagnetic waves in space. Often in amateur radio, you'll hear people talk about frequency in terms of their approximate wavelength. It's useful to be able to convert between radio wavelength and frequency. So we have this formula here. It's wavelength in meters equals 300 megameters per second divided by the frequency in megahertz. This kind of seems a little confusing until we get down here where, say, we're trying to figure out what wavelength or band is the 430 megahertz frequency. So you take 300, again, megameters per second. Megas are going to cancel out, and you're going to end up with, remember, hertz is 1 over seconds, so hertz and seconds is going to cancel out. So you're going to end up with, well, 0.7, but I just converted to centimeters. You're going to end up with 70 centimeter band, and that will kind of ring true for everything here. So we got our bands over here. So just rough 300 divided by, I'm going to round this to 30, is approximately 10. Look at that. We got our 10 meter band. Our 6 meter band, 300 divided by 50 is 6. 300 divided by 150, again I rounded, is 2. 300 divided by 225 is 1.25. 300 divided by approximately 430 is 0.7 meters or 70 centimeters. And then the last one, 300 divided by 900 is approximately 0.33 or 33 centimeters. There we go. This formula is going to be on your exams. You do need to memorize it, and it goes both ways. So if you're trying to determine the frequency, you would have a little bit of algebra here. You'd have the frequency equals 300 divided by the wavelength. So just to show that this is going to ring true, we want to get the frequency of the 10 meter band again, so it would be 300 divided by 10 equals approximately, again, 30. So look at that, 30, we got, it's 28.3 to 28.5, but close enough. None of the exam questions are going to have you do a calculation like this and then kind of get the exact value, although you do need to know these values. And rather than just like memorize them verbatim, I would try and visualize them in a chart, which I'm going to show you. Let's bring this back to something that is familiar to most people. FM radio in your car ranges from 88 to 108 megahertz, so that would actually fall into kind of the 3 meter band. Not a band that we utilize, which makes sense because this is reserved for commercial radio. So when you're tuning into your car radio, say I want to tune into 106.7, which is a radio station I used to listen to as a kid growing up, you're tuned into the carrier frequency, which is the kind of central frequency, and then your radio actually has a bandwidth that it listens to, because remember, in FM radio, you're modulating the frequency, which means the frequency is actually changing. So in this case, let's say that the bandwidth, or the amount of change in frequency, is 10 kilohertz. For FM, or in the very high frequency range, you typically have a bandwidth of 10 to 15 kilohertz. In this case, I showed 10 kilohertz. So you'd actually go down 5 kilohertz and up 5 kilohertz. So your radio station is actually transmitting approximately 106.695 to 106.705. Hopefully this makes sense. Your input amplitude is proportional to your output frequency modulation. And you might ask, why is the bandwidth variable if the frequency is already variable? Like what makes this vary? And it has to do with the amplitude of the input. So if you're getting very loud inputs, Your bandwidth is going to be more towards 15 kilohertz or maybe even larger, although most radios will truncate beyond a certain value so that you're not broadcasting outside of the frequency band that you intended to. So now that we have the hang of frequency bandwidth and carrier frequency, I'm jumping over to this big scary chart. This is the United States frequency allocation of the entire radio spectrum. And what we're going to be concerned with here is this kind of light teal or nice dark teal color. So you can see here amateur has various designated bands throughout the radio frequency spectrum, and you have to stay within those bands because, as you can see here, this is very heavily allocated to many different things. So why does this matter for our current discussion? And that's if you have a carrier frequency that's sitting right at the edge of one of these bands, if you have a bandwidth that's too wide, you could actually drift outside of the frequency that's allocated to you. So you do need to keep in mind the bandwidth when transmitting so you don't tune to the very edge of one of your allocated frequencies. Luckily for us, this big scary chart doesn't really come into play because there's clearly defined bands that we operate in, and even beyond that, your local area will have identified which bands you can use for talk, which bands are set up for repeaters. For most technicians just starting out, the primary bands you'll be using for simplex or analog radio to voice communication is the 2 meter and 70 centimeter band. I made this chart and I will provide a link to it, so that'll be the 2 meter band here and the 70 centimeter band. Notice in high frequency, there's very limited usage for technicians. You can use from 28 to 28.3 and 28.3 to 28.5. So that's pretty narrow. The rest of this grayed out area is it's restricted to general and extra class licensees. And then you can use a little bit of the 80, 40, and 15 meter band for continuous wave only. In the 6 meter band, from 50 to 54 megahertz, you can use continuous wave for that first 0.1 megahertz from 50 to 50.1, and then from 50.1 to 54, you're cleared hot for continuous wave, digital, data, and phone communications. Now, you can take a look at this, download it, print it out, put it by your workstation, because this is very useful. Notice over here is restricted, and then there's actually kind of a portion here from 420 to 430 that if you live above a certain area, it becomes restricted. But beyond that, you do have a lot of frequencies you can utilize. Again, you need to get with your frequency coordinator, which you usually can find all the information online before just tuning into a random frequency and talking, because a lot of them are allocated now, and you don't want to be broadcasting on a frequency that somebody else is using. I touched on this earlier, but I want to reiterate, what is frequency modulation? Frequency modulation is a way to encode information in radio waves by varying the instantaneous frequency proportional to the amplitude of the input audio signal. What does this mean? It means when you talk into your radio, you're projecting frequency and amplitude varying sound waves into your radio's microphone. Your voice is then converted into an electrical audio signal, then processed by your radio before it's broadcast out via the antenna as a signal that is frequency modulated across a bandwidth centered around your carrier frequency. So that's why all of this matters. So it's centered around your carrier frequency. It has a bandwidth. In VHS, that's 10 to 15 kilohertz. Frequency modulation, as the name implies, only modulates the frequency while the amplitude of the signal remains constant. So that comes back up here to this example. Remember, amplitude modulation, the amplitude varies, and that's how they encode the message. And in frequency modulation, the frequency changes, but the amplitude remains constant. FM signal has a carrier frequency, which is the central frequency that your transceiver is tuned to, and a bandwidth, which defines how much your frequency modulates. So again, if you're yelling into your microphone, this modulation will be more towards 15 kilohertz, and if you're whispering, it'll be more towards 10 kilohertz. I'll give another example. So say your carrier frequency is tuned to 145.63 megahertz. This is your carrier frequency, and your bandwidth is, for this example, let's give a bandwidth of 12 kilohertz. 12 kilohertz. Your signal will actually modulate in either direction to 145.624. Remember, so this is negative 6 kilohertz. This is plus 6 kilohertz to 145.636. Does that make sense? It's a total bandwidth of 12 kilohertz, so you're going minus 6 kilohertz here, plus 6 kilohertz here. The bandwidth range of 10 to 15 kilohertz holds true for all VHF voice transmissions. The change in bandwidth is based in real time off of the loudness of your input. Remember, FM converts amplitude of the input proportionally, so input amplitude is proportional. This little fish here is proportional to the frequency modulation. This is a key concept. So the greater the input amplitude, the greater the frequency modulation. And yeah, so modern radios will actually clip the frequency if it strays outside of a designated bandwidth, and this will distort the received audio. So if somebody is saying your transmission is clipped, they're telling you that you need to probably move the microphone further away from your mouth or talk in a more reasonable volume. All right, last bit. Now it's time for the exam. What's the relationship between electric and magnetic fields and electromagnetic wave? The answer is they're at right angles. What property of a radio wave defines its polarization? Remember, there's two waves in a radio wave. There's the electric wave and magnetic wave. And the property that defines its polarization is the orientation of the electric field. What are the two components of a radio wave? I just went over this. It's the electric and magnetic fields. What is the velocity of a radio wave traveling through free space? The answer is the speed of light. What is the approximate velocity of a radio wave in free space? 300 million meters per second. What is the relationship between wavelength and frequency? It's they're inversely proportional, or as wavelength gets shorter, frequency increases. What frequency range is referred to as HF, or high frequency? That would be 3 to 30 megahertz. What frequency range is referred to as VHF, or very high frequency? That would be 30 to 300 megahertz. What frequency range is referred to as UHF, or ultra high frequency? 300 to 3000 megahertz. What is the formula for converting frequency to approximate wavelength in meters? Remember, we did this formula a bunch. It is wavelength in meters equals 300 divided by frequency in megahertz. Remember, the wavelength unit is meters, 300 is megameters per second, and frequency is in megahertz. In addition to frequency, which of the following is used to identify amateur radio bands? The answer is the approximate wavelength in meters. Remember, it's approximate here, and that's what that formula is calculating. What is the approximate bandwidth of a VHF repeater FM phone signal? The approximate bandwidth is 10 to 15 kilohertz. This question is a little bit tricky because it's saying a VHF repeater FM phone signal. The key information is approximate bandwidth of VHF, very high frequency. So that's what you're looking for, and again, for 10 to 15 kilohertz. I hope this was helpful. There's going to be more lessons like this where I'm going to go through all this information and then test you at the end, and by the time we get through the whole series, you should be well on your way to getting your technician